We're going to talk about compound interest problems, which is what you call them when you deal with money, but a larger group of problems we call these exponential growth or exponential decay problems. So let's look at this problem here. Bob invests $1,000 in a savings account, 8% compound interest per annum. Remember, the important thing to remember here is per annum is the Latin for per year. Now, since the ancient Romans didn't contribute too much to mathematics, unlike the Greeks, other than the Roman numerals, we feel a bit bad for them, so we throw in a Latin phrase every now and then in mathematics, just to make the ancient Romans feel good. They gave a lot of other things to civilization, but not a lot with mathematics. So how much will there be after 4 years? So this is the problem that we're going to look at. So let's set this up and look at it 1 year at a time. So if it's going to be 8% interest, obviously the amount he starts with is 100%, that's $1,000. We're going to add 8% each year. And so in other words, we're looking at 108% is what we need to find. Well, when you've looked at percents before, you realize 108%, if we convert that to a decimal, it's 1.08, so that's the multiplier we're going to use to calculate the percent increase. This is a percent increase problem. And that $1,000, when it's a problem like this, we call that the principal. That's how much money you're putting in, although you can use the same technique if you were taking out a loan, for example, for a car or a house or your credit card, which you don't pay off. They deal with compound interest problems just like this. So let's look at it year by year, 4 years. Let's see what happens. So the first year, he invests $1,000, gets paid 8% interest, so times 1.08, and at the end of the first year, he's going to have $1,080. So the compound interest differs from simple interest in that in year 2, he's going to earn interest on this $1,080 he has now. Bob's going to get 8% interest, and that's going to give him $1,166.40. Since this is a money problem, we automatically know we need to round to 2 decimal places. So year 3, he's going to start with $1,166.40. Again, he's going to earn 8% interest, which is going to give him $12.59.71. So you can see the difference between simple interest problem is interest grows a lot quicker when you're dealing with compound interest. So he's going to start year 4 with $12.59.71. He's going to earn 8% interest, which will give him a total of $1,360.49 after 4 years. So this seems to work fine. However, there could be a drawback. What if I wanted to know how much he's going to have after 17 years or after 30 years? It could take us an awful long time if we do this. So let's look at another way of looking at the problem. We start off the same way. Year 1, $1,000. He earns 8% interest. He still gets $1,080. So what I'm going to do this time is instead of, at the start of year 2, instead of saying he has $1,080, we see that 1,080 is 1,000 times 1.08. That's the same as 1,080. So that's what he starts with in year 2. And then he's going to earn 8% interest, which is going to give him the same amount, $11.66.40. So in year 3, instead of writing down $11.66.40, Bob has 1,000 times 1.08 times 1.08, because as we can see from above, that is the same as $11.66.40, and he's going to earn 8% interest, which is going to give him the same amount of $12.59.71. And so in year 4, instead of writing $12.59, we're going to write out our previous calculation. He started with 1,000. He earned 8% the first year. He earned 8% the second year. And he earned 8% the third year. And now this year, he's going to get 8% again. And you calculated that all out. He's going to end up with the same amount, $1,316.49. Now, as you can see, there is a pattern going here. Each year, all we're really doing is multiplying by another 1.08 and then another 1.08. So what I've really done here is I've done 1,000 times 1.08 4 times, which is 1.08 to the power of 4. So that's a much quicker calculation, and following the pattern, if I wanted to know how much he was going to have after 17 years, it would just be times 1.08 to the 17, or 30 years or 50 years is going to make the calculation much quicker. So this is the basic way that we can do compound interest or exponential growth type problems. Now, there is a formula that you may see. I particularly don't like the formula. I think if you understand how this works, then there is no need for the formula at all. But frequently, you're going to see the formula, and you might see it written like this. A is going to be the total amount you're going to have. So it's going to be A0, which is the amount you start with, your initial amount. That's your initial amount, times 1. It's always going to be plus if it was a percent increase problem, R over 100 to the power of n. Now, you might wonder, well, what is this 1 plus r divided by 100? We know to the n is going to be how long or how many years, how many days, how many months it's going to be. R over 100, r is simply your rate. So this should look a little bit familiar. If my rate was 8%, I would be doing A0, 1 plus 8 over 100, and I was doing it 4 years to the power of 4. And you should see that 1 plus 8 over 100, 8 over 100 is 0.08, and 1 plus 0.08 is the 1.08. So that's where it comes from. Again, you don't really need to learn the formula. If you understand how this process works, then there really is no need for the formula. So let's go ahead and look at a couple other problems. Alright, so you've been attacked by zombies. You've had to destroy them. However, your house is radioactive. It falls by 12% every hour. So you should recognize that this is a decrease problem. Now, again, there's no money here. There's no principal. This would be an example of an exponential decay problem. So, again, we're going to start with the same thing. Because, alright, the radioactivity count is 800 counts per minute right now. But we need to find out what our multiplier is going to be. Well, we start with 100%. We're going to lose 12% every hour. So we're going to take away 12%, which gives me 88%. Now, 88% as a decimal is 0.88. So that's the multiplier we're going to use. So the radioactive count is 800 counts per minute times 0.88. So if we just did that, that would tell us how much there was left, the radioactive count after 1 minute. But we're going to, or after 1 hour rather. But we want 7 hours, so it's going to be to the power of 7. So this is definitely one of those type of problems where it's really much easier to use your calculator. And if you put it in your calculator, you should notice that the count after 7 hours is going to be 327 counts per minute. So it's fallen from 800 to 327. So I'll leave it to you to research, well, is it going to be safe after 7 hours to go inside to do your homework or not? That's for you to decide. Let's look at one more example here. So let's say you discover that there were 500 bacteria cells on your toothbrush, and they increase 15% each day. How many cells will there be in a week? Well, once again, we start with what is our multiplier going to be? The bacteria we have on our toothbrush now is 100%. It's going to increase 15% each day, which is 115% of the original. We divide by 100 to turn it into a decimal. We get 1.15. That's our multiplier. So we're starting with 500 bacteria cells. It's increasing So we're multiplying it by a multiplier bigger than 1. And we want to know how many there's going to be after 7 days. So it's going to be to the power of 7, because we're really multiplying 500 times 1.15 7 times. And if we do that, we get an answer of 1,330.00994 and on. Now, even though they haven't said, we're talking about bacteria here, so we probably want to round to the nearest unit. So we would say there's going to be 1,330 bacteria in our toothbrush, unless we do something about it at the end of the week. So these are some typical type problems, compound interest or exponential growth, exponential decay. They work exactly the same way. So what I want you to do is see if you can come up with 3 of your own problems involving exponential growth or decay. Be sure to show a complete solution also with it. While you're doing this, think about, well, what makes these problems difficult? If I ask you to come up with a really hard one for the exam, what would it be about the problem that would make it difficult? What makes a problem a little bit easier? I want you to go ahead and think about those as you work out your problems. We'll leave you with a comic about hand sanitizers that always claim to kill 99.99% of the germs. Good luck on your project.